bad out of the trunk.
Initially. But when we went through this stuff, if we go clear back, we came up with the work energy theorem, right, where we said the net work is equal to the change in kinetic energy, right? So let's put this in perspective again then. Let's say we've got an object on a slippery surface, right? Perfectly slippery surface, no friction. And I'm going to push on it with some force to accelerate it. Well, what are the forces acting on the object then? If we were to draw a free body diagram. So we got this slippery ice coated in WD-40, right? So it's just sliding real easily. Say we're sliding some, I don't know, an anvil or something, right? Some metal object is going to slide on the ice. What are the forces acting on the anvil? So we need gravity. Gravity. Okay, good. Weight acts down. Normal force acts up. What else? Okay, no friction, right? But I've got my pushing force on the thing too, right? Okay, so we got those three forces. What's the work done by the normal force?
They counteract gravity.
Okay, but what's the work done by it? As I push this thing along on the level ice, what's the work done by the normal force? Zero. How come? Because they're perpendicular. That's right. They're perpendicular, right? The normal force is pushing up vertically, and the object is moving horizontally, right? And so it's not doing any work then, is it? None of the force is acting in the direction of the displacement. If you want to get more sophisticated with it and you want to think about it in terms of an angle, theta is the angle between the displacement and the force, right? So it's 90 degrees, and what's the cosine of 90? Zero, right? So no work is being done. What's the work being done by gravity?
Negative zero.
It would be zero also, wouldn't it? Because it's also pointing vertically and the motion is horizontal. So the only work being done is the work being done by my push. Well, what's happening to the object when I push on it? It started at rest and it starts moving, so it's, how would you describe that?
Accelerating.
It's accelerating, right? It's accelerating, it's picking up speed. Well, if it's picking up speed, what's happening to its kinetic energy? It's increasing. Kinetic energy is the energy of motion, right? So it's increasing. So the work I'm doing is creating kinetic energy. It's adding to the kinetic energy. And so that fits with the work energy theorem, right? That is this starting to, now that everybody's finally here, is this kind of coming together a little bit? So the work that we're doing, we're investing in the kinetic energy of this object, right? Okay, let's turn this around. Let's say it's sliding along the ice, and now somebody's going to push on this thing to slow it down and bring it to rest. Okay, same situation, right? The vertical forces do no work. The only force doing work is going to be the push against the direction of motion, right? Okay, does it make sense? Now the force is in this direction, but it continues to slide in this direction while it slows down. So we just said that that's negative work because they're opposite directions. Let's think about that in terms of the change in kinetic energy. It started off with some kinetic energy because it was moving, and I brought it to rest. What's its final kinetic energy? Zero. So the change in kinetic energy was negative, wasn't it? It started off with some positive amount. It ended up with none. Okay, put that together. So how did we accomplish that? Because we pushed against it to take away its kinetic energy, right? What if we kept pushing? So we're going to push against this thing, and it's going to come to rest, and then we keep pushing, and it picks up speed. Now I'm doing positive work, aren't I? Because all of a sudden now the displacement's in the same direction as the force, and it's gaining kinetic energy as I continue to push, right? Okay, so let's do something different. Yeah, question?
So if you were doing, like if you were like slowing it down by pushing it that way, but then you started going back that way, would you have double the work or?
Okay, here's another question that'll answer that. So let's say that I pick this object up off the ground, and then I decide I'm not going to put it on the 2-meter shelf. I'm going to put it on the 1-meter shelf instead. Okay? So how much work did I do?
10.
I did, okay, so once again, it's 100 newtons about, right? I mean 100 joules, right? Because it weighs 100 newtons, but now I only moved it up a distance of 1 meter, right? Well, what about the whole journey though? Does it make sense? Because I did positive 200 joules of work to pick it up to here, but then when I set it down here, how much work did I do? Negative 100, right? So it didn't matter what the trip was it? I could just pick it up and set it on the shelf, or I could pick it up to 3 meters if I was that tall and move it back down 2. Doesn't make any difference, because all the extra work that I invested in by picking it up too high, I gave away by doing negative work when it came back down, right? So what about gravity? What if somebody threw this thing up in the air from ground level and it went up to 2 meters and landed there? If I want to know the work done by gravity, do I really have to consider the whole trip? No, I don't, right? Because gravity's going to be doing negative work all the way up to 2 meters, right? But then it's going to be doing positive work back down to 1 meter. How much positive work? It's going to exactly counteract the extra work it did from 1 to 2, right? It's going to subtract that away when it goes from 2 to 1. So if I want to make this a lot easier, I could only consider, it doesn't matter how the object got from here to here. All that matters is, after the whole story's done, it moved vertically 1 meter, right? Okay, that's what we called, for those that were here, we called that a conservative force. The definition of a conservative force is a force where the amount of work done going from point A to point B is independent of path. It makes no difference. In fact, I could even do something much more complicated. Let's pick this thing up to 2 meters, and I'm going to move it clear over here. And then I'm going to do this with it, and I'm going to go back with it at 2 meters and set it down. If I kept a strict budget of all the work done by gravity, it's still just going to only matter on how much did I pick up here, right? Moving it sideways, gravity did no work because it's acting vertically, right? Over there, when I waved it around, well, it was doing negative work on the way up and just as much positive work on the way down. It's all going to balance out, right? It's like a needle. If you're keeping track of gravity's work, it's going to be negative, and now it's going to get a little more positive and negative, and then, see what I'm saying? It's just going to waver up and down until I set it down, and there it is, right? Now, we said that's an example of a conservative force. What's a non-conservative force? One where, obviously, where the path would make a difference. Friction, right? Because if I wanted to slide this object from here to here, if I push it in that direction, I do a certain amount of work because I'm having to push against friction the whole time, right? So friction's doing work also. Friction's doing negative work by pushing against the direction of motion. If I move it in a straight line, pretend that's 1 meter, and friction is applying 10 newtons of force the whole time. Well, that's 100 joules of work friction did, right? But now what if I do this? What if I go out and take a path that takes 10 meters to get there? The friction's the same. It's still applying 10 newtons of force, but now I pushed it through a distance of 10 joules, or 10 meters, and so it did 100 joules of work, right? Negative 100 joules of work, right? So friction is non-conservative. The path length matters for friction, right? Okay? All right. I think that should kick you loose on any problems you had on the first assignment. Yeah.
So when you're benching, you don't do any work?
No. You don't do it. No, that's right.
That's why
You
it's,
don't,
yeah, it's so interesting that how muscles work, because you move something up, you move it down halfway, like muscle wise, you did a time and a half of work to just like move it up. But you don't-
right, okay, so
you don't
but
have
that's
that
a,
work.
that's a good question though, right? Because obviously you're expending energy, aren't you? Right?
So our muscles are weak.
So how does that work?
Wait, but the other muscle has to
Hey,
get time
no.
to take it back.
Okay, right, there has to be, what's really going on with the muscles? In an intramuscular level, there's something different going on there. Because technically, how much work did you do on the weight? 0. Right, you did 0 because you racked it after you're done. It's right back where it started, right? Okay, but inside, so if your body was built differently, if your body was built so that, let's say when the weight came down, there was some kind of an energy storage system in your body that wound up, wound up some kind of a flywheel or something, and then you could just engage that to push it back up. Well, then you wouldn't have done anything, right? Okay, but because the flywheel would have wound up and then wound down and gone back to rest. That's not the way it works. When muscles work, what's really going on is there's these fibers inside these myelin sheaths that are kind of fluctuating back and forth. And so you have to expend energy to make them slide past each other. And so on an intramuscular level, yeah, you're doing work, right? What's happening as a consequence of that? Well, sure, you're pushing against something, but also there's a bunch of heat being liberated inside the muscle, right? So you are doing work.
That's good.
Yeah, that is good. I mean, moving along, running in a straight line on level ground, technically should be no work, right? At constant speed, because you're not changing your kinetic energy, right? See what I'm saying? But you're moving against friction, right? So you're overcoming friction, and you're overcoming friction inside your muscles when you push something. Okay. Okay. Other thing then. So I'll add a couple more simple machines to the mix here. Okay, so real quick, remind me, what's a first class lever? Where's the fulcrum?
In the middle.
The middle. Okay. So that's a first class lever, isn't it? Okay, what's a second class lever?
On the end with the weight in the middle.
Okay, what's in the middle? The load's in the middle on a second class. So that would be the classic example of a second class would be something like, well, like what?
Like just moving a bolt a bit.
Okay, yeah. I always think of a wheelbarrow as being a second class lever, right? Teeter totter's the first class. What's a third class?
The one where
Okay, effort's in the middle. Okay, so that's like your arm throwing a ball or something, right? The muscle's pulling on your arm right here, but the lever's longer, right? The resistance is up here when you're throwing it.
Speed.
Right, so you're getting speed. Mm-hmm. Okay, so then what's that guy going to be? Pliers.
Class 1.
Yeah, it's class 1. It's 2 of them at once, right? Okay, acting on the same fulcrum. What's nutcracker?
Class 2.
Class 2. And then chopsticks? Class 3. Okay, what's stapler?
Class 1.
3.
It'd be class 3, wouldn't it? Right? How about your arm when you're picking up a weight?
3.
Class 3. Yeah. How about wheelbarrow we already got? Okay. So you got the idea. Okay, so we talked about ramps yesterday. Real quick, how do we define actual mechanical advantage, or we just call it mechanical advantage in our book for any simple machine? What's that? Output what over?
Output energy over input.
Output force over input force, right? It's always how you get actual mechanical advantage. Okay, what is the theoretical mechanical advantage for an inclined plane? Remember, it's in general, what it's always going to be is it's going to be the input distance over the output distance, right? So what's that? How does that manifest itself with an inclined plane then? Like what would the theoretical mechanical advantage be of this ramp that they're using? Mm-hmm.
So your output will be smaller than the input.
Right. What are the
It's like
distances?
Is it kind of like finding the slope?
2.5 over, I don't know what the cross is, but 1.
One, yeah, right here. Over the one, the height, right?
Just 1?
Mm-hmm. Because all it's just going to be all you got to think about is what's the distance through which you are applying the force in this case. You're going to push the barrel 2.5 meters, right? That's the input distance where you're applying the input force. What's the output force? What'd you accomplish? Absent the simple machine, you had to hoist that thing up a meter, right? So when you're all done and you disassemble the ramp, the barrel's gone from the ground to 1 meter above the ground, right? See what I'm saying? Okay.
So it's more force to do that than
So ideally, if it's a perfectly efficient machine, you're going to multiply your force, your input force by 2.5. You're going to have to apply 2.5 times less force rolling it up the ramp than you would picking it up directly, right? Okay. What about something like, let's move on here. What about a wedge, which is just another example of an inclined plane, right, that we use for splitting stuff. When you drive a wedge into a log, what's it doing?
it's using less force to split it than just like bolt.
Okay, so it's multiplying the force, right? It's doing a couple things, but one thing it's doing is multiplying the force. we could measure that, right, if we had sophisticated equipment, so we could measure the forces being applied. But theoretically, what do you think, once again, if we just look at this in terms of how are we going to judge, in this case, input distance and output distance? As the wedge goes into the log, what's the input distance? Well, so it's got to be a lot more, doesn't it, right? Because we're going to trade distance for force. The mechanical advantage of the wedge, for it to be useful, is going to have to be a lot bigger than 1, right? So that means we're getting out a lot more splitting force than we are putting into it, right? Okay, which is true. But how do we see that with theoretically, or ideally, if we look at the ideal mechanical advantage, what are the geometric properties of the wedge? Okay. Think about how far you're having to move this thing through the wood, right? This thing has to move through the wood. The distance, like from here, it's going to be this distance. Oh, where's my pen? Oh, here it is. Yeah. Okay, so this is how far the wedge had to travel through the wood. Agreed?
Yeah.
Okay, so that's what we might call d sub I, right? Well, how far did the
Wood split.
wood split?
Oh, that same amount. Oh, just kidding. That one.
That far right there, right?
Yeah.
See what I'm saying? So the length of the face of the wedge divided by the thickness of the wedge would give you the ideal mechanical advantage, right? Okay, in reality, you think this efficiency is going to be very good for a splitting wedge? No, there's a lot of friction, right? So half the battle here, and don't forget this, I mean, really, a lot of times, the mechanical advantage might actually be less than 1, but it's still worth using, right? Because in this case, how are you going to get in there and rip that thing apart? You're not going to do it, right? I mean, it's too awkward to try to apply force like that, right? If you're trying to pull on that thing, you're having to apply force over a long period. It's just not going to work.
Wait.
Right? Yeah.
If you had something that was like really small that you like drove into it and then like you pressed the button and like exploded, but like shot things out and like broke the wood,
Yeah.
would that be like?
Yeah, you could. I mean, that's what a bomb is, really.
Well, like it wouldn't like explode. It would just like like a
Like a
small like
jack.
hammer, and then it would like
John,
expand and then
John.
like contract.
like a jack, it would go in and then just push out.
Yeah. But
I
like.
mean, you could do that. That's one way you could do it.
Done.
Right. I mean, you
Yeah.
could. You theoretically could have a threaded rod that goes into this, and then when you turn it, it's gonna be like a jack. It's gonna push out. Yeah, you could. The other nice thing about this is it allows you to apply the force in a convenient direction, which is down, and you can store the energy when you're doing the work and you're swinging that sledgehammer. You can store a lot of energy in the swing of that sledgehammer, right? Because you're doing a lot of work on the sledgehammer to push it through that big arc, so you're giving it lots of kinetic energy. So it's going to hit the wedge, and it's going to take all that energy that you stored and turn it into a force that drives, right? See what I'm saying? So it just makes it a lot more convenient. It's a way that you can physically do it. You can use a hard material to drive it through, et cetera, et cetera. But there's a lot of stuff going on there. Only part of the benefit of the wedge is that it multiplies force. Although, if you split a lot of wood, you know that when you're splitting big, knotty logs, there's lots of, it's hard to get through them. You'll have like a splitting wedge and you'll have an axe or something, right? Sometimes you need to get going with an axe, don't you? Right? Because initially you want that axe, which is going to have kind of a smaller angle. How come?
That's friction.
Well,
Not splitting the knots.
you're giving yourself a much greater mechanical advantage when that angle gets small, aren't you? The ratio of input distance over the output distance is going to get a lot larger because the output distance is getting smaller, right? So the smaller the angle, the greater the mechanical advantage. And so when you really got to get that thing started, right, you've got to use something that's got a lot of splitting force, right? So a high mechanical advantage. Once you get a crease going in that thing, then you can maybe drive in a thicker maul or something, right, or a wedge you can drive in with a ball. Okay, you get the idea.
Splitting ball then, rather than being heavier.
Splitting. Well, why do you want that? Because then it's gonna push you through a larger distance, and so you can separate the wood to where it breaks,
Oh, okay.
right? Okay, what about a screw? So a screw, we said yesterday, is that's just an inclined plane wrapped up around a core, right? And so how are we what's gonna be this one you gotta think about a little bit. What's gonna be the ideal mechanical advantage? How are you gonna use input distance over output distance on this one?
Is there friction on the screw and it's corkscrewing up?
Okay, but even just ignoring the friction, if you put a screw, like a wood screw into wood, how are you gonna calculate the ideal mechanical advantage? What's the input distance?
Circumference of the screw.
Circumference of the screw.
It's a 3 revolution.
Oh, how about that? Yeah.
I was like, what the heck are you?
When you turn that screw one turn, what have you done? You've moved it through, you've moved the outside of the screw, right, the outer edge, through a circumference of whatever 2 pi times L is, right? The distance, the distance from the center of the screw to the outside, right? It's gonna be some circumference. When you've turned the screw through the wood, one circumference of the shaft of the screw, how far did it go into the wood? Well, it went the distance from that edge to that edge, right? See how we calculate that then? If we want to calculate the ideal mechanical advantage, it's just going to be, whoops.
Wait, so you want it more on the plane or what?
Okay, so yeah, so if you want to so let's talk about this. This is going to come up when you do, like when you're putting in deck screws, or if you want to put in metal screws or something, right? So the mechanical advantage is just going to be 2 pi L, where L is the radius of the screw, right? Head of the screw, because that's what you're twisting, okay? Divided by the distance between threads, or the amount that the screw advances with one turn, right? So what do you think then? If you want to have a higher mechanical advantage, are you going to want to have a screw that's got a very small thread count, or how do I say that? Like, how would they measure a screw? It'd be a number of threads per inch or something, right?
Yeah.
It's like if you that's got to be what it is, right? It's the number of threads per unit distance.
Wait,
Right?
what is it?
So it's
Thread
gonna.
count?
So yeah, so it's gonna be this. It's gonna be 2 pi L over P, where P is gonna be the distance between that the screw advances with one turn, the distance between threads. So then, if you want to get a really high mechanical advantage, are you gonna want to have a screw that's got a really fine thread count, or it's gonna have one where it's real coarse? Really coarse is gonna mean that there's a big distance between.
Really fine.
Really
Like
fine.
a bolt.
Yeah. Right, so you're gonna wanna get a hardened material on the bolt, right? And it's gonna be then you're gonna have two things that are going on. You're gonna have threads really close together, and what's gonna happen to the angle of the threads? It's gonna decrease, isn't it? You're gonna want the threads, like, you ever notice when you're turning in, what would be an example of this? Think of a place where you'd have to bolt things together that requires lots of force. Like if you're putting, like in a car, I suppose, if you're bolting pieces of the frame together or something.
Half an hour.
Right. Now, if you've had any experience with that kind of thing, it takes a long time to get that screw to go in, right? Because you gotta turn it a bunch of times to get it to move a small distance, because there's lots of threads and they're really small angles, right? If you look at it, you can just see tons and tons of threads on there, right? Dense threads. And so that's gonna pull that thing together with lots of force, right? Does that make sense? Okay, what's the disadvantage of that? Like if you're putting in deck screws, wood screws into
Take
your
a long
deck?
time.
Yeah, it takes forever. It's gonna run your drill down. So you just kinda, when you're doing wood screws, putting together a deck where the forces aren't that big, right? They've got a pretty coarse thread count, and they just go right in, right, with your electric driver. Okay, make sense? All right, so that's a screw. How about, and then if you do something like, you can cheat on this, and you can do what's called a jack screw, which is where you you extend a lever out the top of the screw so that you can really twist on that. So the equivalent that you would use would be something like a socket set, right, where you've got a handle or a wrench that's turning, right? See what I'm saying? But sometimes they're built right into the screw like this, and so it's called a jack screw.
Would that be for really, really, really big screws?
Yeah, yeah. Like when you look at people that were building
It's kind of interesting to look at these old pictures. People that were building like the Brooklyn Bridge and stuff. You know, that wasn't built with power equipment. That was just a bunch of tough guys down there, you know, threading together these enormous bolts. And how'd they do that? Well, they just had really big wrenches that they turn these things with. Okay, wheel and axle. Okay, wheel and axle, there's a way you can think about this that really helps, I think. Think about a wheel as just being an extension of a lever, right? So let's just say that we're going to put a fulcrum right there, right? And we want to pick this weight up, let's say, right? So one way we could think about this is we've got a lever that's going to extend from there out to there. Everybody see that? And so I'm just going to, if I want to pick this thing up, would you agree that if I push down on this lever right there with a small force, it's going to multiply that and give me a very large force there? See what I'm saying? Okay, but the problem with the lever is, once I tip this thing down, well, it's not going to work very long, right? I can only tip it down so far before the line is going to run into the fulcrum or something, right? So what do we do instead? Well, we just attach a bunch of spokes maybe instead, right? So we got a lever there, and then there's another lever there that we keep pushing on, and then that one will catch the line. Well, that's just a wheel, isn't it? Right? Those spokes just get joined in the form of a wheel. So we just got a continuous surface out here. By pulling on this edge of the wheel, we're effectively always pushing straight down on a lever, right? It's a continuous lever. And then it's always providing a force straight up on another lever, right? So that's really all it is. It's just like a continual lever. Wheel and axle. You see that? Yeah. Okay, so then finding the ideal mechanical advantage of a wheel and axle is really simple, right? It's the same thing effectively as it was with levers. Didn't we say that the ideal mechanical advantage would just be the input distance, which is going to be the effort arm, divided by the output distance, which is the load arm, right? Well, in this case, what does that become? What would we call that for a wheel? What is that input or the effort arm?
Where it is.
Yeah, the radius of the drive wheel, right? The one that you're applying the force to, right? And then the output arm, or the effort, or the load arm would just be the radius of the work wheel, right? A lot of times you'll call this the, this is the slave wheel, and this is the drive wheel, I think. That's what you call that. Does that make sense though? So what's an example where you'd want to have a large mechanical advantage?
Pulling a log up a hill.
Okay.
Pulling an engine out.
Pulling an engine out of a car. And what about a car without power steering? Right? A car without power steering, what's probably going to be true about the steering wheel? It's going to be big. Yeah, it's going to be big because you got to get a big mechanical advantage to turn those rubber wheels against concrete in a big car. You got a big mechanical advantage there. Right.
So like in a car, like you want the axle, like the wheel to be as close to the tire size as possible then?
The axle size?
Like,
Well, no, okay. So, but then, okay, where's another? So then, to turn the thing, right? And you've got a strut system that's going to make the wheel turn, right? So that's different than turning the wheels of the car, right? All you're doing there is you're turning the angular orientation of the wheels. So you want a mechanical advantage to be able to move them that way. But if you want your car to be fast, which we do, where's an example of where you would want to have a mechanical disadvantage?
That's right there.
Well, but say it again. Yeah, so where do you want to have a wheel and axle working where you're going to want to have a mechanical advantage much less than one? At the axle, where the axle joins the tire, right? Because the engine can turn the tire with lots and lots of force, right? But you want to be able to translate that into lots and lots of speed. And so if you look at like a dragster, what do you notice about the radius of the tires on a dragster? They're really big, right? They're really big because you got this dragster that's turning this enormous axle, this hardened steel axle. And it's got an abundance of power, abundance of force that it can input into that torque, right? But you want to convert that into as much speed as possible, so you make the tires really big. So you'll trade force for distance or force for speed, right? Make sense? Okay. One other one that's not talked about in the book that comes up. Oh, what about a pulley system? I'm just kidding. I mean, that one's. I'll get some pictures for you. But if you think of a pulley system, in fact, let me
Let's
just
just go make one.
let's go make one. You know, actually, I've been planning one. I want to do one for track really bad. I want to do an ultra speed pacer where we can do overspeed training. So the way that's going to work. Well, here I'll show you how that's going to work. Yeah, here I'm going to draw a picture. Seen from above, here's what the ultra speed pacer is going to be that I'm going to build for our sprint team. It's going to look like this.
Yeah, for next year.
No, for this year. I think I'm gonna do it this weekend. Seriously. Now we're entering the time of the year where we need to do this a little bit. So all we're gonna have is we're gonna have a fixed line right there. So F for fixed, right? It's gonna go out to a pulley out here, like so, and the pulley is going to be. This one is gonna be attached to the coach, to the slow coach, right? So that's me, and here is the sprinter, right? This one is fixed in place. Either it's gonna be tied off on the starting stand, or most likely we'll just have a couple of these and we'll have another athlete just holding that one stationary, right? Okay, so the coach, what am I gonna do?
You're gonna run.
Oh, the post, right. So what I'm gonna do, if I want you to get some overspeed training in, where you're gonna get tugged
Oh,
with
you're
just
gonna
a little bit.
slingshot him around?
No, I'm just gonna pull this way. I'm gonna pull that way with very little force. And I don't wanna create lots of force. You only wanna create, even for Kate, I only wanna probably pull him with 20 pounds of force tops. We don't wanna change his top speed by very much. We just wanna challenge the central nervous system to accommodate a little different level of speed, so that's how you get growth for the central nervous system, axonic growth, all that good stuff. So that's gonna make him that's gonna make him faster, but I'm not nearly as fast as Cade. So there's two things going on here. The force is not a big issue here because I don't want to pull with very much force anyway, but I'm old and slow and he's young and fast. So I got to be able to move a lot more slowly than Cade, and I've got to be able to control the amount of force that I'm applying to him. So this is an ideal way to do it. I've got a movable pulley, right? So if there's a movable pulley there, do you see that, like, if you were to, as I move this way, let's say I move from there to there. Well, what has that done to him? That means I've added that much extra to that distance, but I've also had to shorten this one by that much plus that much. Do you agree with that? Because the total length is the same, isn't it? Let's say this is a 100-meter cable, and that's starting at 50. Well, if I move 10 this way, then this one becomes 60. So what does this part have to become? 40. Well, it started up, see what I'm saying? See how that's gonna work? Okay, for that to become 40 there, how far did he move? He had to move 20, didn't he? Right, because now the total distance, that's 60 and that's 60, so the net distance is 120, right? You get that?
Yeah.
So we're getting, that's a mechanical disadvantage for me, right? Because I'm gonna trade force for speed, right? You get that? Okay. Right, but that's a way you
So
can
which
use.
way is he running?
Same.
So he's running here. I'm tugging him along, and he's going that way. But I only have to go half as fast to control it, to give him that extra push.
But I don't
See what I'm saying?
understand how it's like creating resistance for
How it's creating resistance. So I'm going to be pulling on this one's fixed, and I'm going to be tugging on this, right? I have to tug with twice as much force, but I'm going to get twice as much distance for that. I'm going to get twice as much speed for that.
But what is it doing for the runner?
Oh, it's gonna assist him in running, so it's gonna make him run a little faster than he normally
It's
can.
gonna propel him, right?
It's like
Oh.
pushing him while he's running. It's like pushing him while he's running at a straight pace.
Mm-hmm. But it's a safe way to do it, and you can do it. There's some criteria, physiological criteria when you're sprinting. You want to be on a level surface, and you want to be able to control it, and you want to be able to do it for a short interval. So this is a way where you can do all those. You can check off all those boxes, right? So then let's take a different example of a pulley system then. Let's say we have one like this. Let's say you want to pick up a car engine, right? If you want to pick up a car engine, you'd use a block and tackle, right? How would you do that? Well, let's say here's the ceiling of the shop, and here's a pulley right here. You're going to pull down on this, and then this is going to go up, and it's going to wrap around a pulley there, and it's going to go down to the engine, right? And there's going to be a pulley there. It's going to go up, and it's going to wrap around another pulley up here. and come down and wrap around another pulley and so on and come down and attach to the engine, right? So I got a bunch of movable pulleys and fixed pulleys here. Do you see that when I pull out, like, how many are there? 1, 2, 3, 4, 5. If I pull 5 feet of cable, how
That's
much is that
25
engine
feet.
going to move up? 1,
Oh,
right? Because if I pull 5, that 5 feet of pull is gonna be split among all 5 of those separate strands that are connecting the roof to the engine, right? So that's theoretically, that's a mechanical advantage of 5. I've gotta pull 5 times as much line to raise this thing up, right? But what's the benefit of that? 5 times less force. Plus, I get to use my own body weight. I get to pull down on it and use my own body weight to lift it up, right? So that's hugely advantageous. So then if we want to calculate the ideal mechanical advantage of a block and tackle system or a pulley system, what do? It's really simple. 1, 2, 3, 4, 5. We count the number of lines that support the load, right? Would you agree this is the input line? That's where I'm applying my force, right? But that force is transmitted through all 1, 2, 3, 4, 5 of those lines that connect the ceiling to the block, right? And therefore I get 5 times the force. Isn't that genius? Right?
I saw one of those, a handmade too. Fell on my friend.
Yeah, and that's what you'd see, like if you even look at a crane or something, like an old crane where it uses a bunch of cables to pick up the bucket, that's all it's doing, right? Okay, last thing. This one doesn't show up in the textbooks, but it's really interesting. If you want to excavate, let's say you want to move something really heavy, or you want to excavate big rocks and things, what do you do? What do you use?
A big bucket.
An excavator. Well, how does what's the principle on which the excavator works? You know? Yeah, but what's the system always that what is it? Hydraulics. It's hydraulics, right?
Is that air pressure?
No,
No.
hydraulics, not, and you would never want to use air pressure because air is a compressible fluid, and so if you use air pressure, you'd be storing this tremendous amount of energy in the air, which is like a bomb, right? I mean, one way you could build, in fact, this is kind of interesting, the very first, I just learned this recently, when Lewis and Clark traveled, they made their long trip from east to west, they had some really high-tech guns with them that they used for hunting. They were air rifles. No kidding. It was like the first, it was more efficient for them to use air rifles than it was to use gunpowder at that time. So they would compress this air, store the energy in the air, and that's how they would launch the musket balls. What's that?
How big compress air?
I think it was like a bellows. It was like a bellows where they could compress it, and there was a seal in there. And so that's how they did it. I never would have known that, but so you could, that's what an air rifle is, right? An air rifle is just using the force stored in that compressed air to push a BB out the end of the gun, right?
Or like when you cock like a BB gun?
Yeah, that's what you're doing.
Yeah.
You're storing, you're doing work on the gas, which is storing that as and we'll look at that stuff later.
Is it like in a water gun? Yeah. Like a water gun looking at that?
Well, water gun's different. Water gun, you have to squeeze it out. It's not as efficient in a way because you can't store the energy. You have to push it all as you push the water out. You're having to provide the energy as you do it in real time. Unless you pump up an air chamber that's going to store it and then push the water out with air.
Yeah.
Right?
And she's like, I'm not gonna judge. Fire.